All right. Let me share my screen. So, assignment 2 due Wednesday the 10th, so Wednesday next week. Any questions on this so far? Again, please get started on it as soon as you can. Don't don't wait until until the day before, because it won't happen too easily for you. So essentially, we covered what to do with number 2 at this point. All right. So let's move on with the lecture. So we started talking about last time translating English language statements into predicate logic statements. If this is still behaving, it is. Okay. Consider some large domain D, so it's something more than what you're typically talking about. So in general, you can consider it to be like the whole universe or something like that. And then we want to write a predicate logic statement with the same truth value as an English language statement when propositional logic is insufficient. So over domain D. That's when, so propositional logic doesn't suffice when you have quantification going on with your statements. So there's two main principles for doing these translations. Okay, the first principle is whenever universally quantifying over some subset of your large domain, you write as follows: for all x, p of x implies, where p of x identifies the subset you're discussing. Okay, so in order to exclude the rest of D, so p of x is, here we have h of x. So, for example, h of x is a horse, b of x is brown, d is the whole universe. So you want to say all horses are brown. You don't want to say everything in the universe is brown. You want to say all horses are brown. So in order to disregard things that aren't horses, you use the implication statement. So for every x, if x is a horse, then x is brown. Okay. If this is true, then this statement is true. If this is false, then this statement is false. They have the exact same truth value. I'm not saying it's true. I'm not saying it's false. Just they have the same truth value. Okay, and remember, the only time an implication is false is when the hypothesis is true and the conclusion is false. When the hypothesis is true and the conclusion is false. In other words, when you're talking about a horse, X, that is not brown. A horse that is not brown. We don't care about anything else. Anything else that isn't a horse makes this statement already true. So those things can be disregarded. So all horses are brown. Looks like that. For every X, HX implies BX. Another common construction: no horses are brown. Well, when you say no horses, you mean something negative about all horses. So all horses are not brown. The same thing as saying no horses are brown. Although this is more succinct, and so people will typically say that instead. So all horses are not brown looks like that. For every X, HX implies B not X. Only horses are brown. This is a little bit trickier, this only construction. Only horses are brown. Nothing else. Just horses. Okay, not dirt, not bears, not chocolate, not whatever. Just horses. So something is being quantified universally, and the thing that's being quantified universally are brown things. Right? To say this as an if-then statement, only horses are brown, it's the same as saying if it's brown, then it's a horse. Or in the contrapositive, if it's not a horse, then it's not brown. So that looks like this. For every X, if it's brown, then it's a horse. Or for the same thing by a contrapositive, the equivalent statement, for every X, if it's not a horse, then it's not brown. So notice the universal quantification always goes with implication. Universal quantification always goes with in the hypothesis. Universal quantification in the hypothesis always goes with implication. It never goes with conjunction. Universal quantification never goes with, never goes purely with conjunction in the sense that we're about to talk about here. Now, existential quantification goes with conjunction. So when you want to existentially quantify the set of your large domain, the universe, you write, sorry, somebody say something? All right, so there exists X, Px, and whatever property you're talking about. So if you had P of X means X is a potato, B of X means X is brown. To say some potatoes are brown is there exists X in the domain such that X is a potato and X is brown. Some potatoes are brown. Not all potatoes are brown. So not all, the negation of universal quantification is existential quantification. Not all potatoes are brown. In other words, some potatoes aren't brown, or there is a potato that isn't brown. So it looks like this. We'll talk more about how you negate quantifiers later. By the way, this is different than no potatoes are brown. No potatoes are brown, so don't confuse this with not all with, well, not all something. Not all somethings with no something. Well, I shouldn't use the word some, should I? Not all widgets. Not all widgets with no widgets. Don't confuse not all widgets with no widgets. Not all widgets is there is a widget that doesn't. Not all widgets do something means there is a widget that doesn't do something. No widgets do something means all widgets don't do that thing. Okay? Subtle difference. But in a logical sense, it's a big one. Subtle linguistic difference, but in terms of logic is different. So this is existential. This one is universal. All right, let's take some more examples. Oh, warning. Forgot to do the warning. Never write for every x, p of x, and blah. Why? Sorry, p of x and this. Why? One would never say a statement like this in English. One would never say a statement like that in English because, when people talk to each other, you only bother to make a statement when what you're saying is somehow controversial. Controversial meaning that, well, we're not sure if it's true or false. We need to discuss it, right? So, not controversial as in, some violent controversies like what goes on these days, but controversial in that, we don't know. Maybe it's true, maybe it's false. We need to think about it a little bit. This one, there's no controversy. It's just what? It's just what? This statement. I don't care what P of X means. What's the truth value of this statement? True or false? In other words, a domain that doesn't include just things identified by P. I mean, if you want to say everything in the universe is a potato and everything in the universe is a potato and everything in the universe is a pony and everything in the universe is purple and such a statement is just what? Not everything in the universe is identified by P, and this is conjunction. Such a statement is what? True? Such a statement is true?
False.
It's always false. It's always false. One would never say something of that sort. Nobody would say everything in the universe is a potato and blah blah blah. Everything in the universe is a potato, and I don't care what the and is. It's false. Not everything in the universe is a potato. Okay, as long as P is not the whole domain. If P is not everything in the domain, if your domain is all numbers, all real numbers, you would never have P of X is a number. Because if your domain was just P, you wouldn't bother specifying it again. Okay, let's talk about numbers. Let's talk about the domain of all numbers. Now, take an X in our domain. X is a number and. Again, you wouldn't say it. Unless you're really, trying to state the obvious. Just some things are, such things are just not said. So, the point of this is universal quantification goes with implication. Universal quantification goes with implication. It doesn't go with conjunction. Never goes with conjunction. Except in the following sense. This is when P of X is conjunction, and then you have a parentheses here. If you have something like this, you can write, however, something like this. All right, so P of X is a potato, and B of X is brown. So for every X, P of X and B of X implies. So the thing here is that there is a parentheses here that's understood. Not like this. All right, this is a statement that says, something like, all brown potatoes all brown potatoes taste great. All brown potatoes, can be baked. All brown potatoes can be mashed. All brown potatoes are fun to juggle. I mean, whatever it might be. That's different than this. This is everything is a potato and statement. Okay, because it's in parentheses here. If you're just trying to hook together identifiers, something identifying potatoes and something identifying brown things, and you want to identify brown potatoes, you put them together like that. Okay, so that's warning number one. Warning number two. Warning number two, never write. There exists X, P of X implies, parentheses. Why? Again, when you make a statement, you're somehow, describing something whose truth is in question, somehow controversial. Right? You don't say things that are just, true by some flub of logic, some vacuous flub of logic. We typically don't talk like that. So this type of statement is always what?
Always true.
It's always true. Why?
Is it because that X is always...
Well, there is an X that's not in your big domain, or an X that's not a pony, or an X that's not purple. There's always something that isn't. So something in the universe is not a potato. Therefore what? Therefore it doesn't matter. When the hypothesis is false, the implication is
true.
True. When the hypothesis is false, the implication is true. How many times do we need the hypothesis to be false? Just once. If we can make the hypothesis false just once, then we have our existential thing that makes this statement true. So, I mean, you just said something that, is just logically, true just by some, vacuous form of logic. Which is just not the way we talk, really. So, existential quantification doesn't go with implication. It does go with conjunction. Universal quantification goes with implication. It never goes with conjunction. So, couldn't be easier, these two principles. Right? If you're saying there is, you better be using conjunction. If you're saying all, you better be using implication. And never the other way around. Okay, the only sort of like mix of the thing is when you do something like this. For every brown potato, and you don't have an identifier for brown potatoes, but you have an identifier for potatoes and an identifier for brown things. Then you put them together with conjunction. Potato and brown means brown potato. That implies something. But the parentheses is around the conjunction, not conjunction and then parentheses. Okay, examples. It seems weird at first, but it's actually not so bad once you get the hang of it. So P of X is a pony. G of X eats grass. R of X runs fast. D is the whole universe. Okay, so let's do some translation. All ponies eat grass. All ponies eat grass. Quanta. So write the corresponding predicate logic statement, the same exact truth value over the domain that is the whole universe. All ponies eat grass. All ponies eat grass. So for all x, g of x. For all x, x eats grass. Is that it?
It would be P of X implies G of X.
P of x implies g of x. Not for all x, g of x. That means everything in the universe eats grass. Right? So, if you're not an ungulate, I hope you don't. I guess ducks too, right? Ducks and geese. So P of x, G of x. If it's a pony, then it eats grass. Right? You can say all ponies eat grass if you want to say it as if then. If it's a pony, then it eats grass. No ponies eat grass. Say it as an if then. So this is equivalent to if it's a pony, then it eats grass. How about this one? No ponies eats grass. Say it as an if then.
If it's a pony, it doesn't eat grass.
If it's a pony, it doesn't eat grass. Or if it eats grass, then I guess I should put the then, right? Then it's not a pony. And linguistically speaking, though, the then isn't always strictly speaking strictly necessary. You can kind of leave it out. Then it's not a pony. So one or the other, right? They're contrapositive of each other. This is G implies G naught. This is G implies P naught. So no ponies eats grass. So if it's a pony, it doesn't eat grass. If it's a pony, it doesn't eat grass. Or if it's a grass eater, it's not a pony. Not all ponies eat grass. Not all ponies eat grass. Well, not all isn't universal quantification anymore.
Is it there is an X for all of X in the domain?
No, there exists X in the domain.
Okay, and then just G of X implies P of X?
But you never put implication with existential. It's always conjunction.
Oh.
So not all ponies eat grass. Remember, not all. So this is equivalent to. Not all is equivalent to some ponies don't eat grass. So not all ponies eat grass. That's PX and G naught X. So there's at least one. So some ponies, what? Don't eat grass. It has to be conjunction. So some things are ponies and don't eat grass. How about this? If a pony eats grass, then did I give it? Oh yeah, then it runs fast. If a pony eats grass, then it runs fast. What's being universally quantified here?
The pony.
Not just ponies.
Oh,
Ponies that eat grass
Ponies
run
that eat
fast.
Yeah, ponies that eat grass run fast. So it's for all X. What?
So P of X and G implies F of X
Whatever. Yeah. So there's an implied. I mean, you don't have to put the parentheses there because of operator precedence. Okay, but you can write this. You just can't write this. Right? P of X and then the statement. So this can't be your ultimate connector. Here, this is the ultimate connector, the last connector. It can't be that the conjunction is the last connector with the thing you quantified universally. All right. Only fast ponies eat grass, not cows, not buffalo, not ducks. Just fast ponies eat grass. Not sheep, not goats. All right, this is equivalent to what? Say it as an if-then.
If it is a fast pony, it eats grass.
Only fast. That is, fast ponies do eat grass, but it doesn't leave out goats and cows.
If it eats grass, it's a fast
It's a
pony.
fast pony. If it eats grass, it's a fast pony. If it eats grass, then it's a fast pony. So that leaves out everybody else, right? So this is for every X. If it's a grass eater, then it's a pony that runs fast. So those are some basic sort of ways that if-then implications and conjunctions are used with universal and existential quantification. Things get more interesting when you start involving two variables. So examples with two variables. So B of X is a B. F of X is a flower. And LXY is X likes Y. All right. All bees like some kinds of flowers. All bees. Okay, so all bees. All bees are yellow. All bees are striped. All bees make honey. All bees sting. Whatever it might be. Just saying all bees means what? I write again.
For all X.
Universe. I'm sorry, you were just gonna say it. For all X. For all X what? So forget about this for a second. Just all bees. How does it start now?
So, B of X.
All bees. What's the
Like some kinds of flowers.
Forget about what this is. Just let's.
Okay.
For all X, B of X. Since we're universally quantifying bees, it's
Implies.
yeah, implies. So let's just start it out like this. So all bees. ... It just looks like that. Okay. So now we'll take this. All bees like some kinds of flowers. So it's all bees again. So all bees implies. Implies what?
Some kind of flowers.
You like some kind of flower. If it's a bee, then it likes some kind of flower. So flowers being quantified how?
Would that be L of
well, first
BX?
Quantify, right? There's some kinds of flowers. So there exists Y. Now, because the scope of this quantifier is everything between here, you can't re-quantify the X. So I have to introduce a new variable for the Y. So there exists Y. There exists a Y, that's what?
That's a flower.
That's a flower. Connector. What about that flower?
And all bees like it.
Well, we've already got our B quantified, so X is
Oh.
yes, you're on the right track. So
X1.
LX1. Another one. For every X, if X is a B, then there is a Y that's a flower, and X likes it. So all B's like some kind of flower. Now, whatever flower it might be depends on the bee. This bee likes roses, that bee likes violets, this bee likes jasmine, whatever it might be. All right. Every bee, if it's a bee, for every X, if X is a bee, then he's got a flower he likes. So all bees like some kind of flower. Now, this can also be written with this quantifier up front. This can also be written as for every X there exists a Y. Linguistically, it's a little more awkward, although notationally it is a little bit more compact. For every X there exists a Y such that if X is a bee, then Y is a flower and X likes Y. Right. Suppose the statement is true. Suppose it is true that in the universe, every bee likes some kind of flower. So let's pick a bee for every X in the universe. So for every X in the universe, so I'll pick this hornet over here. So X is this hornet. What happens to this statement? So pick X. X is a hornet. What happens to this statement?
It becomes false.
It becomes, this becomes false. So the statement becomes
Oh, true.
true. Right? So again, with the implication, you forget about everything that's not identified in the hypothesis because it's already vacuously true. So for every X in the universe, okay, if that X is a B, so for every X in the universe, if X is a B, there exists some Y that makes this true. Well, here's Buzzy the bee, and every bee likes some kind of flower. So you ask Buzzy, hey Buzzy, what kind of flower you like? Buzzy says, I like jasmine. So Buzzy is a bee, and jasmine is a flower, and Buzzy likes jasmine. So this is true, and this is true, so the statement is true. For every X, whether you pick Buzzy or Buzzy's brother, or his uncle, or whatever else. Okay, suppose it's false. Right? Suppose you live in an alternate universe where, bees just don't like flowers. Some bees don't like flowers. Well, I guess that actually is true, right? I mean, not all bees. It's only the ones that make honey or something like that, right? I don't know. Anyway, I'm not certainly not an expert. So, I mean, maybe there's some species of bee that just doesn't deal with flowers at all. Right? So, in which case, if you take that funny, weird species of bee, it's a bee, but there doesn't exist any flower that he likes. He just could care less about flowers. So that would make this true and that false. So it makes the implication false for some bees. Okay, so we see that the truth value here and the truth value here and here, now these are actually the same. What the difference and why you would use this or why you would use that's something we're not really covering in this course. Linguistically, this makes more sense. But sort of from a computational logic standpoint, this makes more sense. But that's something we cover in computer science classes, not really here. All right, all bees like some kind of flowers. All bees like all flowers. All bees like all flowers. Every kind of bee, he likes whatever kind of flower you show him. Well, again, it's all bees. All bees. So how does bee
Exists a Y for all X?
all bees. All bees and all flowers. No existential here.
So,
All bees.
all X, all Y.
Okay, well, we can do it that way. For all X and for all Y. Well, all bees and all flowers. So if, say it as an if then. If, for every X and every Y, if,
So B of X implies LXY.
well, you need to figure out if it's a flower, Y. You need to identify it as a flower. You were just saying, BX, LXY. That means all bees like everything.
Oh, so it would be BX implies FY and LXY.
Implies LXY.
Okay.
Yeah, universal quantification always goes with implication. So if it's a bee, so again, it's all bees, right? This can be written like this for every X. It's all bees. So for every X, like I was saying up here, all bees. For every X, B of X implies. Implies what? implies that X, he likes all flowers, not just some of them, all of them. So for every Y, F, Y implies L, X, Y. Can you say it without all the implications, with just one implication? So it could be written like this. It could be written like that. There's another way to say it. Just one with just one implication. Remember this from the homework? P implies Q implies R is logically equivalent to P and Q implies R. Remember that one? Can you apply that here? So B implies F implies L, right, is the same as B and F imply L. So you can also say it like this. If X is a bee and Y is a flower, then he likes it. All of these work. All right, we're universally quantifying bees and universally quantifying flowers. So for every bee and every flower together, you know that bee likes that flower. Right? All bees like all flowers. Or for every X, if X is a bee, then he does something. What is that something he does? He likes all flowers. For every Y, if Y is a flower, then he likes it. If Y is not a flower, we don't care. We're not interested in that. All right. It's weird at first, but go over these notes again. Okay, go back to these examples that we're doing, after class, and look at this statement. Start with that one, and then, write down the answer as you see it, and then check it here, and see if you got the same thing I got, and try to understand why that's the answer from, a deeper level, just analyzing the implication, how the implication works. And go through those examples again, and it seems weird at first, but it's not. It makes more sense once you've done it. Once you've got more practice. Sorry. All bees like all flowers. Okay, some bees like all flowers. Well, some bees, dot 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 dot. Some bees do something. So some bees make honey. Some bees sting. Some bees fly.
There exists some X.
P of X connector. What's the connector with existential?
Conjunction.
Conjunction, yeah. There exists X, B of X, and. So whenever you see some bees, you can just write that. And then go from there. So some bees like all flowers. Some bees like all flowers. Well, okay, we're starting out with some bees. So I can write what? How do we start it out?
For all flowers, so for all Y. No.
Oops, I didn't want to do that. Some bees. B's.
There
X, B of X,
exists
and.
B.
So that's how we started out. Right? There exists X, B of X, and. I'm not, so concerned about what the and is. Just the fact that we started out with some B's. So some B's do something. Just there exists X, B of X, and. Now, let's talk about the flowers. Some bees like all flowers. Which flowers? All of them. So how am I going to quantify now? There exists X, B of X, and what's the quantifier now?
Would it be all? So like that A thing.
Yeah, for all. For all Y. For all Y, what? What Y's are we interested in here?
F.
Yeah,
Of X.
flowers.
F
All Y. If it's a flower, then what? What's X's relationship to that flower?
LXY.
LXY, and connectors implication. Some bees like all flowers. Can be written like this, or if you want, can also be written as there exists X for all Y, B of X, and Fy implies LXY. So you can have that connect the quantifier here, okay, or it can be here. Either or works. But you have to have that parentheses here, by the way, because there exists X such that X is a B and something. So that something is in parentheses. Some bees like all flowers. Some bees don't like some bees don't like flowers. Which ones? There are some bees that don't like flowers. Which flowers don't they like? Some roses or all of them? Some bees don't.
All of them.
Period. All of them. Some bees don't like any kinds of flowers at all. Don't like flowers. Stay away. Again, some bees. So I just write what? We're starting out with some bees.
There exists bees.
Yeah, there exists X. So that X is a bee. And what? Now, what are we talking about and how do we quantify it? We're talking about flowers. And how are we quantifying the flowers? Some bees don't like some kinds of flowers. Some bees don't like any kind of flower. What are we saying here? What's this sentence saying? I mean, if I said to you, I don't like chocolate, does it mean I don't like Hershey's bars?
Some bees don't like all flowers.
Don't like all flowers, right? If you say I don't like chocolate, I don't like chocolate, it doesn't mean I don't like Hershey's bars. I mean, it does mean that. It implies I don't like Hershey's bar, but I don't like any kind of chocolate. I don't like Hershey's, don't like Cadbury, don't like Belgian, whatever it is, Don't like chocolate ice cream, chocolate cake, no kind of chocolate at all. So some people don't like flowers. So that's all the flowers. So for every Y, what? What kind of Y is we talking about here? Chocolate Ys or flower Ys? Or any kind of Ys? We're talking about FY. Connector
Implication.
implies, yeah. Implies what?
L not XY.
L not XY. There it is. Same as this, just there's a not here. So this is some bees like all flowers. So there exists an X such that X is a bee, and for every Y, if it's a flower, he likes it. Some bees don't like any flowers. There exists an X such that X is a bee, and for every Y, if it's a flower, he doesn't like it. Okay. We'll do more examples of this next time. Definitely try to get started on this. We've got this, number one here. You should be able to tackle that one, or if you're not sure about it, we'll go over some more examples. Okay. So instead of bees and flowers, we got farmers and vegetables. It's a nice example. All right. Okay, so I'll post this, and I'll get your homework assignment back to you next time, hopefully, and we'll see you on Wednesday. Okay. Email me with any questions or concerns.